So spherical aberration is a big function of shape factor. So in this case, the light is only being bent at one surface, so there's a lot of spherical aberration when the shape factor is -1. In this configuration, the light is being bent at the two different surfaces, so it distributes the refractive load, and there's much less spherical aberration. This is a biconvex, which will have somewhere in between. From the pre-lab, we determined that for an object at infinity, the best shape factor is 0.7.
At the beginning of this lab, we first aligned our laser to a secondary rail, or a shorter rail than we normally do, so our laser is lined up to this rail using a pinhole. And then we placed a mirror on a second rail to bend the laser beam 90 degrees. We then had to align the laser beam to this new rail. And it's the same way we would with the laser. We adjusted the tip tilt of the mirror and used a pinhole, sliding it back and forth. The final step was aligning a microscope to this new rail, and to do that we just made sure that we adjusted the tip tilt height and left and right so that the crosshairs and the light spot shown on the original beam position.
So these are some important notes about the setup that we have. One, we chose to use a mirror instead of a pentaprism because for us it was easier to align the tip tilt to align the system. We also have this L setup because we can have the mirror on a translation stage, which moves this beam along the microscope. And it's easier to do it this way than translating the entire laser. We have the pinhole here during when we're taking measurements to stop down the size of the beam so it fits through the Shack-Hartman holes easier and doesn't overlap into other holes. Also, on the microscope we have translation stages in both X and Z because for our measurements we're measuring longitudinally and transverse. This is a schematic of the system we're using. So these holes represent the Hartman test and the lens, and this shows the spherical aberration. So when we're at marginal focus and translating along the X to take the transverse spherical aberration, as we go from hole to hole it moves in one direction. Then when we're looking at, when we're translating along the Z direction and looking from hole to hole, we see that it moves in one direction, and then as we go the other way, it moves back.
So for this part of the lab, we sent the laser through the started the laser in the furthermost extreme hole, the rightmost extreme hole of our Hartman screen, which is set up here with a plano-convex lens with the plano side facing this way to get a shape factor of -1, which will increase the spherical aberration as we are trying to observe spherical aberration. We then navigated the mirror this direction, moving the laser's spot through each hole, and then this changed where the spot was on here, and then we would adjust the microscope to find where the spot is and record both the location on this micrometer and on this micrometer. We can use that to calculate the lateral spherical aberration. Alright, so this is our data for our lateral or transverse spherical aberration. This column has the location of the mirror laterally. This column has the location of the microscope laterally as we moved it through each hole of the 11 holes. We then had to normalize it to these two sets of data so we could see the actual absolute distance rather than the relative distance. And this curve is the data we plotted of our lateral spherical aberration.
As part of the lab, we found the longitudinal spherical aberration, and so to do that we had to find the paraxial focus compared to the marginal focus of the lens. Now, the paraxial focus is a bit hard to find because when you have the laser passing through the center hole in the Hartman mask, it is already at paraxial focus. So what we did is we started at an outside one and slowly brought the laser through each hole, and then brought the microscope forward or moved it along the rail so that our spot was at our original position.
This is our data as we moved the microscope longitudinally to find longitudinal spherical aberration as we moved our microscope along the z-axis. This is our data here. You can see that the peak of the parabola is actually somewhere between holes 5 and 6, which makes us think that the center of the lens is actually in between those two holes rather than right on the center hole. This is our data for the last part after we flipped around the lens. The red curve indicates the lens flipped around, which would have a sphere or a shape factor of 1, whereas the original data has a shape factor of -1. Theory indicates that you should get less spherical aberration with a shape factor of 1, which indeed proved to be true, as once normalized, the red data has smaller peaks.